So this is the lecture on a thermal expansion and will be the final lecture we have on thermal properties of the lattice on our course in solid-state physics. So what we will do here in this briefer lecture than usual is that we will formulate a treatment to understand the thermal expansion of a solid from a microscopic point of view. And we will learn how the changes in the interatomic potential that we have, that is describing the movement of atoms, how the changes in this potential play a role, and how it is in fact the asymmetric shape of the potential that is actually important in the process. And like I in the previous lecture mentioned, that thermal expansion is actually a process where we need to extend our treatment beyond the linear approximation. We now see that in the microscopic point of view, it's really the asymmetric shape of the potential that gives rise to the nonlinearity of the system. So that gives the asymmetry that then gives rise to thermal expansion. And similarly, you could also make the thought experiment with yourself and realize that this would also be the mechanism that would give rise to nonlinearities that would explain, for example, the photon scattering processes that we mentioned briefly in our lecture on thermal conductivity as a main limiting process of thermal conductivities of solids when we go to higher and higher temperatures. So this is what we will do here. We will formulate a treatment to understand thermal expansion, and we will formulate it from the macroscopic point of view, and then we will look into the microscopic potential as a kind of originator of this nonlinearity. And let's start with a little bit of motivation. And okay, this is that we want to understand how thermal expansion takes place in a solid. And of course, it's a microscopic thermal expansion we are interested here to understanding. And we know from high school physics that all macroscopic objects, they expand thermally. And some examples would, for example, be an Eiffel Tower, radio masts in general, and then also for the cables that are attaching, securing the radio masts in place. And these things that it really matters, especially in Scandinavia in the summertime. In wintertime, the temperature difference is quite big in the end, so that when engineers are designing things and some people are then actually fabricating things and manufacturing things, these things must take into account. So large buildings, we must take into account the thermal expansion with long cables, certainly with railroads and bridges. And I think another example would be the wheels of a train and how they are being secured underneath the train. Is that because trains are so heavy, we cannot really use normal bolts and nuts to secure the wheel of a train, but instead, like the wheels are being put into place into a more solid piece of a rod by heating up or cooling down the wheel and the barrel accordingly. And with that, it's possible to actually change the dimensions of the wheel correctly so that it can be slipped into its position. And when the system is being restored to the room temperature conditions, then it will be securely tightened, the wheel there, and it can rotate. And this helps to actually come up with a wheel structure that is mechanically rigid and strong enough so that it can actually support the weight of a train with the speeds the train is moving. So that's another example, and I think there's maybe even an example in a high school book about this. What else? High precision instruments. So I'm thinking of pendulum clocks out of their historical importance here. So that's where we used to have at least a very important thing to remember and to consider was the thermal expansion of materials. So really back in the days and in 1900, the high precision instrument that was being used was actually like a pendulum clock. And in a pendulum clock, it was really the change in temperatures of your ambient surroundings that mattered the most into the precision of the clock. So pendulum clock, it's essentially a harmonic oscillator, and we know that the oscillation of a harmonic oscillator depends on the length of your pendulum, and if the length changes, then the oscillation frequency also changes, and then your time, how do you measure time, changes, and you have these kind of inaccuracy in precision in your measurement because of this. And I think it was that in 1900, in the early ones, there was really a revolution in high precision instruments and timekeeping due to the fact that it was found a material that did not expand thermally that much, and that gave rise to a possibility to build clocks that were quite accurate, like from the previous understanding. And by the way, if I remember it correctly, pendulum clock, if you know what I'm speaking, please, if you don't Google, I think they were already, they were an old invention, maybe even like Galileo or Newton, maybe they already knew it at the time, or they were like inventing them, or like developing them for their purposes. Like if you want to make astronomical observations, it's good to also know the time when you're looking at into the sky as accurately as possible, because otherwise you cannot really know the position where the celestial object is if you do not know time accurately. So another example, like satellites, of course, they are not big objects, but in space, the temperature changes are quite dramatic depending on whether or not sun is shining. It's a gentle radiation into the satellite. And are you on the warm side of the satellite, or are you on the dark, cold side of the satellite? So the temperature changes are quite dramatic. And because of this like a temperature difference between the different sides, this must be taken into consideration when these kind of objects are being made. Bimetallic thermometers, so essentially those wiggly thingies in our saunas, if you have some, please remember that that's based on thermal expansion. So we have two metals, as the name suggests, bimetallic, and then because the thermal expansion of the other metal is different, and when they're sandwiched together, the whole thing will curve, and then if you make things correctly, you can then relate this curvature with the temperature, and you can secure a needle into this curved piece of a bimetallic wire, and then the needle will point in different directions depending on the temperature. So that's a very easy way of making a thermometer. So these are some of the examples, and there are many other ones, but they, maybe from the engineering point of view, I really recommend you to look into the high precision instruments, pendulum clocks, and the history of them. It's really cool piece of history and physics, I would say. And from our point of view, why we are speaking of thermal expansion in a course on solid state physics, this is quite nice process, because now when we are looking at the microscopic picture, we really need to introduce the anharmonicity of our system. So we really need to look into the form of the interatomic potential function, and we realize that this is in fact where this macroscopic process then originates itself. And as always, like when we are looking at some macroscopic phenomena, there must be a microscopic explanation of that phenomena. So that's what we are looking into here in terms of thermal expansion. So we start by defining the coefficient of thermal expansion, alpha, and we define that through an equation that we are looking at a relative change of the length of our solid, and we start with the solid that has a length L, and then the delta L is the small change when we are changing the temperature. And this gives us a possibility to define alpha, the coefficient of thermal expansion, by just multiplying alpha with delta T. So this is the way that if we change the temperature, let's say 10 degrees, and we know what is the alpha, then we see that it will give a small change in the relative length of our solid that originally in the kind of first starting point temperature is of a length of L. Or another way of defining things is that, of course, we can define alpha as a 1 over L times the relative change of our object with respect to temperature. So that's the kind of like maybe a more formal way of defining the coefficient of thermal expansion. So we have 1 over L, the length of our object, with respect to the change in the length of our object with respect to temperature changes. And this is fine as long as we are looking at a small changes in the temperature. So the change is still linear, but of course in reality it may not be linear always, so that we should be careful when we are using alpha. We should not just mindlessly apply it to too large changes in the temperature. So delta L divided by L is the relative change of the length of our solid, and delta T is the small change in the temperature, with emphasis on the word small, because this is an approximation. We are just assuming we are linearizing our system, and we are interested in just the first contribution. But of course, when we go beyond in the treatment, we would realize that alpha is actually not just a linear parameter. In practice, it's often quite small, so it's of the order of 10 to the power of minus 5, 1 over kelvins. And this material INVAR, it's a nickel iron-based alloy, and this is exceptionally, this material has an exceptionally small alpha value. And this was discovered by Guillaume, C.E. Guillaume, and he was awarded a Nobel Prize in Physics in 1920 for this discovery. I think Guillaume discovered INVAR in 1895 or something around that time, before 1900. And the reason why this finding was awarded a Nobel Prize was that it really led to many breakthroughs in many precision instruments. And this was from the fact that it was then possible to make more precise clocks than earlier. So INVAR-based pendulum clocks had an accuracy of around 10 millisecond deviation from the real value per day, and these clocks served as the time standards until 1930s, when the electronic clocks started to replace these. But this was really a very important invention, and Guillaume was being awarded a Nobel Prize because of that. So I think it's a nice example of the kind of like a technological development. And of course now, time standards, how time is measured nowadays is that everything is done optically. So now we have atomic clocks where we are looking at is it like cesium atom? I don't remember exactly, but the precision nowadays, it's something unbelievable. I think it was like 1 second in a few 100 million years that is the kind of deviation in accuracy in time. Maybe it's like 1 second per 300 million years that these atomic clocks, how precise they are nowadays. So a lot has changed since 1900 when INVAR-based pendulum clocks were invented. So here I'm now hopefully able to show you some material table and some representative coefficients alpha for the different materials. For example, lead, we have 2.9 times 10 to the power of minus 5 as the alpha value. With aluminum, a same order of magnitude. With copper, similar order of magnitude. With glass, we see that we are already having a little bit less of a thermal expansion. And here, finally, we have the INVAR, and really we can appreciate the fact that the alpha value is an order of magnitude or 2 orders of magnitude less than other materials, conventional materials. And if I recall correctly, you can even purify INVAR further so that you can make even better materials based on that. And I think INVAR is still being used in applications where, for example, you may need to have you need a material that needs to be working at very different temperature ranges. So especially at cryogenic applications, I believe INVAR is still a material that is being used quite a bit due to its thermal properties. And next, what we will do is that we will start looking into the microscopic understanding of what happens. And in order to qualitatively at least understand what happens in terms of thermal expansion, we will start looking into the interatomic potential. And how do we look into it is that we will make a Taylor's expansion of the potential, and we have already done this. So we see that the formula and the functional form of an interatomic potential, it's roughly that we have the phi value at the equilibrium position A, and then we take the first derivative divided by 1 over explanation mark times r minus A, and then we have the second derivative, so basically the curvature of the potential now matters, and then we have the higher order terms. And please remember that it was first that the curvature that gave rise to like physics we have considered so far, and please note that this potential is related to the restoring force. So when we are looking at the phononic vibrations, lattice vibrations, it's the curvature that matters here mostly, and we see that we have the force, restoring force giving rise lattice vibrations is equal to the minus gradient of our phi. And here we have seen that the third term, which is related to the curvature, so the third term, this guy here, gives rise to the elastic behavior of solids. Recall chapter 3 and the mechanical properties. And now what we must consider here is that we must also look into these higher order terms. And we also have higher order contributions that are non-zero, and even though in some cases they may be small, now when we are looking at the thermal expansion, they are not small anymore. And because of that, is that we actually have an asymmetric potential, and similarly we will have an asymmetric restoring force. Please recall functional forms, for example, these simple functions. If we have y equals x squared, and how that differs from y equals x squared plus, for example, 0.1 x cubed when we are looking close to the equilibrium position. So we see that there will be a slight change in the shape of our curve when we go to higher and higher of x values. And what this means is that when we are looking at the temperature dependence, we are putting a little bit more of thermal energy into our system, and we are calculating what is the mean position of our oscillator. What's the mean position? We see that the system can now shift its equilibrium position because we have this anharmonicity in our potential. And I will stop my lecture by just showing this roughly, graphically speaking, how this process may take place. So let's start by recalling the equipartition theorem, because that gives us the understanding what happens when we increase the temperature. And the equipartition theorem says to us that the mean energy of our oscillator, we are just considering a one-dimensional oscillator, the mean energy will be kpt. So please recall from the equipartition theorem that we get a 1 over 2 kpt value of energy per each energy degree of freedom. So we have a one-dimensional harmonic oscillator, so we have a 1 translational degree of freedom, and we have the 1 potential degree of freedom. So 1 over 2 kpt from each degrees of freedom, so that 1 over half plus 1 over 2, we get 1. So that's the mean energy of our oscillator. And when we go to higher and higher temperatures, what happens is that these oscillators, they turn into anharmonic ones. And when we go to higher and higher temperature, what then happens is that the potential, when we are close to the kind of original equilibrium position, because we do have thermal energy in here, and the thermal energy is being stored in the oscillations of atoms with respect to their equilibrium position. When we have a low temperature, the potential still seems to be harmonic, and we do not have asymmetry much here on this region of the slope. The mean location giving us basically the kind of interatomic distance, the equilibrium distance will be unity value here. And this is the kind of like a low temperature or starting point temperature here. And now when we go to higher temperatures, recalling equipartition theorem, we know that the thermal energy is being stored in the oscillations of our oscillators. And now, because the shape is asymmetric, what happens is that when we are calculating the mean position, the asymmetry starts kicking in, and this mean position does not remain in the same location anymore because the potential is not harmonic, but rather it starts shifting to the longer values. And this is what happens when we increase the temperature at just high enough values, and then we see that the mean distance between the adjacent atoms actually increases. I have exaggerated this situation dramatically here. I don't think there will be any material that actually like increases this much. The separation increases this much, but it's rather very small, the change. But this is of course related to the fact that the alpha values are very small usually. But at least this is the process that happens. And interestingly enough, I think this is quite a cool piece of physics. We see that it's really the shape of the potential function that then matters here, and then that gives rise the thermal expansion we see in a macroscopic picture. But in a microscopic picture, it's really yet again the interatomic potential function phi, and essentially its anharmonicity. And then we also were able to use the equipartition theorem here, so I'm pretty happy of the outcome of this lecture. So I'm now done with this lecture 4.4, and also I'm done with the section 4. So we have now covered the basics regarding the thermal properties of lattices, and here our treatment has been really mostly based on phonons. We have discussed a little bit about impurities and how they affect. We have mentioned phonon-photon scattering processes, that they also play a role at some point. And in terms of materials, please think that here, chapter 4, we have elucidated quite a bit of the properties of dielectric solids. Because in dielectric solids, we do not have conduction electrons, but rather we will have physics arising from the lattice contributions. And from that point of view, I think and I feel that the thermal properties are the kind of easiest starting point to understand how dielectrics behave, how the other properties also behave. And next, we will also start looking into the electronic properties, and there the emphasis will be more on metallic properties, metallic solids. Please recall or appreciate the fact that when we look into the electronic properties, we will essentially be using very, very similar models as we have used to understand phonons. So although we do not right away say that we are going to be treating harmonic coupled oscillator systems in our treatment when we want to understand electrical properties, that's what we will be heading forward in that description too. So this is quite universal. This piece of math we have used to understand lattice vibrations. So that's also being used later on when we look more into the physics of solid state materials. So I thank you for listening, and please enjoy the rest of the day or night or morning, evening, and I will stop here and start making my playlist on Diamond songs. Thanks and bye bye.